So this video is on the properties of rational functions, and we're going to start with those properties and then move right into finding the domain. A rational function will always be in this format. It will be written as a fraction, because that's what rational comes from, is ratio of two things, and it's going to be a fraction of two polynomial parts. Now remember, in a polynomial you can't have a fraction. So this is not a polynomial function. It is made up of two polynomial functions. The other thing you have to remember in math is that if we divided by 0, we would have an undefined spot or an area that doesn't exist. So we must also state that the denominator cannot equal 0. And so our domain for rational functions is all real numbers except that the denominator cannot equal 0. So given a situation where I have this function, it is written in the format of 2x squared minus 4 over x plus 5. This is a rational function. It's a polynomial function divided by a polynomial function. And when we look at this, you have to ask yourself, what would cause my denominator to become 0? In other words, if I set the denominator equal to 0, negative 5 would create that situation. So my domain is that x cannot be negative 5. In other words, negative 5 is a number that does not exist within this function, because negative 5 plugged in here would make 0 in the bottom, and we cannot divide by 0. So let's take another function, looks a little different. It's still a polynomial divided by a polynomial. This particular function, though, is not in factored form. This is in simplified form. So if I take that polynomial and I factor it to x plus 2 times x minus 2 in the denominator, I now have two factors, x plus 2, x minus 2. Both of them have a degree of 1, which means they have a multiplicity of 1. And we're going to need that later, so keep that in mind. Then we can state that if I had x plus 2 equals 0, then x equals negative 2 would cause a problem. And x minus 2 equals 0, then x equals positive 2 would cause a problem. So my domain would be that x cannot equal positive or negative 2. The third one that I want you to see is in this format, x cubed divided by x squared plus 1. Now, the denominator, if we were to try to factor that, we would find out that that is not factorable, because x squared plus 1 equals 0, x squared equals negative 1. I would have to take the square root of a negative number. And although we learned in section 4.3 that negative numbers, or the square root of negative, makes it imaginary, which is a number we're allowed to work with, rational functions stay in the real numbers only. And since this would be imaginary, this would create plus or minus I, we can ignore this. This is imaginary, and so we can ignore that as a restriction, because the domain exists over the real numbers, and so the domain is still all real numbers because there's only imaginary restrictions, and we're allowed to ignore those. Okay? The last one is if I had this is equal to x squared minus 1 over x minus 1. When we look at this, the top can be factored, and we're going to factor it later. But for our purposes, for right now, since we're just finding domain, I want to point out that even when we factor this, x plus 1, x minus 1 over x minus 1, I know that's going to factor out. But it's still a restriction. It would still cause me a problem if x minus 1 was equal to 0, and therefore if x equaled 1, I would still have a problem. So my domain is x cannot equal 1. Now we've been going through all of these and we've been finding domain restrictions. Well, domain restrictions show up in our graph in one of two ways. Domain restrictions either show up as wholes or asymptotes. Now, a hole is literally a gap in the graph, and the problem that we just worked on, where we had x plus 1 times x minus 1 over x minus 1, and I said this canceled out. That is going to create a hole on the graph of x plus 1. Now, you know x plus 1 is a linear graph, so I'm just going to go through and graph x plus 1 like that. But the difference between this, x plus 1, and the graph of the original problem we started with is that right here, when x is 1, there's going to exist a hole on my linear function. And so to graph the original problem, I think, was x squared minus 1 over x minus 1. It would look like the line x plus 1. See what's left when we simplified. It would look like that line, but there would be a hole right here at 1. Whereas an asymptote is a behavior. An asymptote, a vertical asymptote, is always written in the form x equals some number, and we'll call it some number a, okay? And that comes from our restrictions as well. So let's take this problem that we had 1 over x squared minus 4, and we turned that into 1 over x plus 2, x minus 2, and we had a domain restriction that x could not equal 2 or negative 2, right? Well, when I graph this, there's going to be an asymptote behavior right here at negative 2 and right here at positive 2. This is x equals negative 2, and this is x equals 2. Now I want you to notice I put can't equal in domain, but it is equal in my asymptotes. I've got x equals negative 2, that's the equation of a line right there, and x equals positive 2, that's the equation of this line right here. And what's going to happen on this is that if I were to graph this particular function, and I will tell you I know some point values here, that if I plugged in 0, I would get negative 1/4. And so when I plug that in, the graph is actually going to go towards that asymptote and run towards the ground. And it's going to do the same thing on the left-hand side. In other words, it will never cross the vertical asymptote. This graph is going to run towards that asymptote and then run to the ground or run up to the ceiling. We'll talk about how we know what it does later. But right now you have to recognize that for vertical asymptotes, it will never cross. I was going to write never go across. That's why I started with a G. It will never cross a vertical asymptote. Your graph will never cross a vertical asymptote. It's always going to run towards it and then either shoot off to the ground or shoot up to the sky. So what I want us to practice for the rest of this video is how do we find vertical asymptotes. So if I gave you this function, f of x equals 5x squared over 3 plus x, you start by telling me the restrictions. And I know that in this case, 3 plus x equals 0 would be bad. So x can't equal negative 3. That's my domain restriction. But the asymptote, the vertical asymptote, is x equals negative 3. So on my graph, I would go to negative 3, x equals negative 3, and I would draw a vertical asymptote just like that at x equals negative 3. Okay, let's do another one real quick. We should have time for one more. X minus 1 over x squared plus 5x plus 4. This would be x minus 1 over x plus 1 times x plus 4. And my vertical asymptotes would exist here at x equals negative 1 and here x equals negative 4. So where do we look for vertical asymptotes? In the denominator.